Gulf of Maine. We are over here somewhere. And so it's got this beautiful shape. There's actually some really interesting geology as to why the Gulf of Maine formed, and I'd be really happy to talk to you about it if you're interested in the formation of the Gulf of Maine and why we have the biggest tides in the world. But that's another day. So this is the blue channel. Here's the green channel. Here's the red channel. These are all on the same scale. And what can you say if black is 0, white is 1 times 10 to the minus whatever. These are radiances. What can you tell me about how the ocean behaves in terms of being a pure absorber or pure scatterer within different wave bands?
Pure absorbing the red?
Yep, because of water absorption, right? So none of the light, basically none of the light except for right around Grand Manan, which is a really great place to be. The ocean looks pretty black. Okay, what about the other wavelengths?
It reflects the most in the blue.
It reflects the most in the blue. So we have some mid-range here and even some pretty bright stuff offshore, which means that it's bluer offshore, less blue inshore. What about in the green?
Absorbs in some places and reflects close to the coast.
Yeah, look at, this is the Bay of Fundy. And look at that. It is really, really reflective. Because there's a lot of water and resuspension, huge tidal currents. And so it's very, very, very bright in the green in those. Okay? Cool. I have no idea where we are. Oh, okay. Sorry. So this is another one of my favorite images. Lights off for another favorite image. Phytoplankton blue in the Barents. So here's Norway. Is it gorgeous? So we see all of this incredible features in the ocean, and they tend to be variations of blue and green. Like here's really dark blue, and here's light blue and greenish. And it is due to this infinite combination of absorbers and scatterers. And our job, your job, is actually to collect data from places like this with remote sensing to get a spectrum of light and to tell us what's in the water. By measuring that spectrum, you should be able to tell us something about the absorption features, something about the scattering spectrum, and then what that tells you about the material that's in the water. Are they big particles, small particles? Are they living? Are they detrital? Are they pigmented? And if so, what pigments? All that information is right here. And that's your job. Well, it's all of our jobs, but for this month, it's your job. Okay. So, Emmanuel, is this clock right? Where is Emmanuel? He just left. Is that clock right?
9:57.
Okay. All right, good. All right, so I want you guys to make absorption and scattering in the forefront of your brain every time you look at the ocean. So as you look at the ocean and you see how bright it is and you see the color, I want you to always be thinking, like, oh, clear and green. Ooh, turbid and green. Those tell me two different things. So I will tell you in the wintertime, the Gulf of Maine is clear and green, even into the spring. Later in the summer, it gets turbid and green. It never gets blue. We'll figure out why as we go. Okay, so always look at the color. Blue to green, sometimes red. That's a sad thing when that happens, sometimes. Clarity, is it clear? Is it turbid? Can you see the particles? Is it bright or dark? Think about those characteristics, and we'll begin to interpret them in terms of optical properties. All right, so those are the IOPs, absorption, scattering, and beam attenuation. You'll have lectures on all of these. They have really easy math. A plus B equals C, I have no idea. I'm sure somebody in the back knows the history of why it's A, B, and C. Ken's like, nope, no idea. Is it because it's just so easy?
It used to be A for absorption, S for scattering, and alpha for absorption, S for scattering, and C
E.
as beam attenuation.
Or they used to like extinction.
Yeah, and then there was an international Committee convened to straighten out the notation. So they came up, and like, for example, radiance, which is now called L, used to be M. And so this international committee, which had, for example, Henri Morel, who was French, he campaigned that radiance in French is luminance, so it should have an L. And absorption should be A for absorption. And some way they then came up with, well, let's do A, B, and C for absorption, scattering, and attenuation. And it's been a mess ever since.
Yes, it has.
And of course, if you go to atmospheric optics or somewhere,
Totally
they've
different.
got entirely different notation and terminology. It's even worse.
We tried to put together a little table. Do you remember back in, I don't know which class, we were like, we're going to get it clear between the atmosphere and the ocean. It just really wasn't worth it. Okay, so these properties, absorption and scattering and attenuation, are dependent upon the stuff in the ocean, the particles, the dissolved substances. They're independent of the light field. And when we talk about light field, we mean the solar light field. And that's because they are inherent properties of the water that you can measure. If you take that water and you bring it into the lab, you can still measure its properties because we measure them with a light source. The sun is not our source. And so that's why we mean inherent properties. Okay, so this is Clark Little. He's a photographer in Hawaii. That's his arm holding his camera. He's very famous for all sorts of wave pictures. Here he is for a different wave. So, what can you tell me about the water in those two different places?
Different colors.
They're different colors. We've shifted from blue to green. So some things absorb the blue light. Okay, what about this one? Absorbed all the blue light, all the green light, maybe all the yellow light, most of the yellow light. And what we're left with is red light. Okay. And what about this one? Oh, right. Ah. I actually went to his gallery during one of the Oslo meetings, and I wanted to meet him to say, like, you could write a textbook for optical oceanography with these photos. Well, we could write the book, and you could put the pictures in. So this is, of course, the plumes of sediment coming up, and you can see the scattering is really different. And when you have a very short path length, you can see the sky through the water. So you're not actually seeing the color of the water here. But it's stunning. Okay, apparent optical properties. So these are the ones that are derived from radiometric properties when we measure radiance and irradiance. You can, they can be properties from above, like reflectance. They can be within the ocean, looking at how light disappears with depth. You calculate them from ratios of radiometric properties and gradients of radiometric properties. So they do depend on the light field. The sun is our source. We are actually measuring how the sun reflects off the surface or is transmitted through the surface. You don't measure them with an independent light source. That's why they are apparent optical properties. But they also depend on the IOPs. The reflectance and the attenuation properties depend on what's in the water. So the three that you'll learn about, and Kurt mentioned these, you'll learn about how sunlight penetrates, hence this diagram. We use something called the diffuse attenuation coefficient to describe how light is attenuated with depth. We can look at the angular distribution of light, which we talked a little bit about earlier in the atmosphere. You can see these beams of the sun, but as you get deeper and deeper, the light gets more diffuse. So the angular properties have changed. And that tells you something about the scattering, right? So if you could measure how the angular distribution of light changes with depth, you could infer something about the scattering properties of the particles in the water. And then reflectance is one of the surface properties. So you can look at how bright the ocean is or how dark the ocean is and what color it is and have that tell you something about the properties. Okay, so the last thing I want to do today, so basically doing 4 weeks in 90 minutes, actually an hour. So we have a little bit of vocabulary. So we want to go back to this beam of sun, but now this is our beam of sun that is transmitted through the surface. You could trace one of these rays. And I want to think about what's happening to that. So imagine that you have a sensor that can measure that beam. So we have a sensor, we're measuring that beam. We're going to measure that beam all along its path as a function of depth, right? So we could start off up here, and then we'll measure it here and here and here and here, okay? I want you to describe what happens to the beam. I want you to think about its intensity, its color, its direction. What is going to happen to that beam as I measure along this path? You can describe it, you can sketch it, you can do it schematically, you could graph it, you could write an equation. But I'm going to give you until 10 o'clock. No, yeah. 3 minutes. Work with your partner, sketch something out, and we'll go through it. All right. That's all you get. Okay. All right. So we're going to call that beam of light radiance, luminance, L. And that light is traveling along that path. And one of the things we have to think about is that that's coming in at an angle, right? So it's coming in at an angle relative to the vertical. And it's also coming in at some angle relative, the azimuth angle, right? So we've got an angle down, and maybe we were looking at it in this direction, or maybe we were looking at it in this direction. I'm going to ignore this right now, just because it won't fit on the slide. But we're following that angle down, okay? And so when we talk about what processes impact the beam, what are going to be some of the processes that we have to think about? Absorption, scattering, fluorescence, okay? So absorption does what? It reduces it, right? So I drew a smaller arrow. Okay, so as we travel down that path. And then what is scattering going to do? It's what? It's okay, you can just make sure that everybody can see you. It's going to do that. It's going to scatter out of that path, right? So as this light is traveling down, we're going to lose energy as we go, right? So what's going to happen to this arrow then? It's going to get smaller, right? So we have scattering out of the beam, and that arrow will get smaller. I put a lot of scattering, so it got really small all of a sudden. You think of anything else that scattering can do?
Can you say others also to the electromagnetic?
Yes, you can get scattering into the beam. So you can have light that was coming down this path at these angles, get scattered into this beam and increase the light. And we'll talk about the relative contributions here. I've drawn them as equal. Ignore that. Okay. It's a schematic. Okay. And then we have inelastic scattering. So we could have light that was coming from a different color. And since I started off in the bluish green here, I had to start off light coming in from shorter wavelengths from the ultraviolet, getting absorbed by, say, color-dissolved organic matter and getting re-emitted into our color that we're measuring. And that is going to do what? It's going to add, it's going to make that, it's going to add into that wavelength. So it's taking energy from one wavelength and adding it into the other wavelength. Okay. So you can see that it's kind of complicated. What happens as we measure this? But I think you've done a pretty good job putting the pieces together, right? Did anyone have anything else that I missed? So this is fluorescence by CDOM. We could have fluorescence by chlorophyll, but chlorophyll doesn't fluoresce in the blue. But if we were in a red wavelength, it would be taking energy from the blue and green and putting it out in the red, and you can end up with more red light at depth than you started with from the sun. So we would have to do this for every wavelength. Okay? So pick your wavelength resolution. Say we want to do from 400 to 750, and we want to do it every nanometer, so we'd have to have all those arrows, different colors. We also should make sure we consider all the different angles, right? So you can see how complicated it gets. Okay. All right, so what we've done here is we've talked about how radiance changes along this path, right? DLDR. And I've just done the zenith angle. I've ignored the azimuth angle. I leave that to others to derive that. But often we don't really follow the radiance down like this. We follow the radiance down like this. Right? So we're going to convert from this path R to depth, right? And we can do that if we know the angle. And so we do, because we've done geometry. And so we can now instead say, okay, we're going to look at the radiance coming in at this angle as a function of depth, as long as I know the cosine of that angle. Okay, so now we're looking at the gradient in irradiance with depth. Okay. So the first thing we said was absorption. So what is absorption? What is that going to do? How would we express absorption as affecting the change in radiance with depth?
Decreasing exponentially.
It's going to decrease exponentially, decrease the light exponentially. But if we just look at like little bits, so it's going to be decreased, so that's a negative sign. We have something called an absorption coefficient, and we want to know how much radiance is lost, so we can just multiply them, right? Just multiply them. This is how much radiance we've lost. Whew. Okay, what about scattering out of the beam? Scattering is termed B. Gain or loss? loss, so minus sign. And we just multiply it, right? Okay, cool. That's that term. What about scattering into the beam? It's going to be a plus. Yes, definitely a plus. What do we have to keep track of? Yeah, which one? So it came from some other angle, some other theta, right? So we have to keep track of that angle. And then what else do we have to keep track of? Yeah, so if it comes in here, we have to figure out how much scattering coming in at that angle is going to scatter into that angle. So we have to know where it's coming from, and it could scatter in any direction, but we only want that one, right? So you have to keep track of that angle. Right, so it's a little more complicated. And you have to integrate over everything.
How can we know the angle?
Well, because you have to know what the radiance is at every angle. You're not just doing one, you're going to do all of it. Don't worry. I promise you'll get there. It's exciting though, right? I know. I get excited. So, oh, wait, and then this one. You had a question.
Yeah, why is, in the integral, why do you integrate over theta? Radius is radius.
Because I ignored the azimuth angle, and so I'm assuming that there's some symmetry. But you have to integrate. So, good question. We have to keep track of all angles, light coming in from all angles, and for every radiance coming in at one angle, we have to keep track of all of the scattering angles. And we have to do that for light coming from this direction, scattering in here, light coming in this direction and scattering here. So we have to add it all up, all the effects. We have to add up the effects of all the radiances coming from all different thetas that are going to scatter from that angle into our angle.
Well, then why are you integrating over theta and not theta prime?
Oh, thank you. Theta prime. Thank you. Excellent. Perfect question. Theta prime. Yes, but that's how we do that, is so that we can keep track of where everything is, how everything is getting in there. Okay. What I have to do here? You need a wavelength term. So I need to keep track of light at all the wavelengths shorter. And I need to know the efficiency by which material can convert light from one wavelength to another. And I kind of need to know how that material absorbs light and all the wavelengths that it absorbs. And then fluorescence emission has some angular distribution. So I have to keep track of that too. So I just said we need to know the absorption. We need to figure out how much light was there to be absorbed. Then there's a lot that happens in here, in that arrow. And that's going to give us the radiance at our wavelength at our theta. But there's a lot that goes on here in terms of wavelengths, fluorescence efficiency, and angular distribution of fluorescence. It's much scarier than that, but you can do it. All right, so that's all of our terms. You've just derived the radiative transfer equation. Congratulations. Okay, I think my work here is done. Yeah, okay. Radiative transfer in the forward direction, have your dragon, predict your tracks. And then later, we will measure the tracks and we'll predict the dragon. And we'll be able to apply it to this beautiful image, if that is the image of your choice. Okay, we're done. What do we do now? We ask for questions. Sorry. And then we can go outside because the sun is outside and we should go outside. Yeah, quick. Go out and measure the sun. Do you have your radiometers ready? All right. Thanks, guys. We'll see you. Oh, wait. What? Do they have questions? I'm here all week. No. What time do we come back? 15 minutes. Great. Excellent.
And then you're really out of the room and then they get a picture of everybody. You guys are like walking out if you want to take a very good picture of you in front of the wall out here. So we can get a little guide for everybody. Don't worry about looking your best. It's just for
Or brushing your hair, which didn't get to. Uh-oh, did you miss something? Oh, the chair. Oh, I don't know how to do those. Is it too high?